Hi everyone, this is Billy. Today I'm going to show you my latest invention, the Jacket Crystal Radio. So you're watching the prototype. It's mounted on the shoulder and there's a coil beneath the jacket. Later on I modify it to a stiff version, so you won't be able to see that there's a coil and the coil is hidden underneath the jacket. For the purpose of showing the video, I just mount the tuner on top of the jacket, but you can always keep it inside the pocket. If it's the first time you watched my channel, this is the Billy C DIY channel. In this channel, I will share with you everything that I made, including hydroponics, crystal radios, electronics, retro handheld machines, and many other stuff. I need your support if you like my videos and my inventions. Please click like, subscribe, share with your friends, and don't forget to click the bell so I can inform you when my new video or my new inventions is out. Keep on watching. We'll talk about how to make it and then we will test it at the end of the video. Thank you. Before we start, a bit of warning. If you try to test this crystal radio jacket, make sure you test it in an area where you're under full control. That means you won't be mistaken as a terrorist or someone carrying a bomb. Because with wires all over you, people may think you're hiding something dangerous. So warning, don't try it out unless you have full control of your environment for testing. Hi, let me show you how you can make this jacket crystal radio. So this is the jacket. We'll be sticking a coil at the back of the jacket later on. And this is the coil. This coil is made using some printer flat cable. Let me zoom into the connection point for you. So this printer flat cable has thin copper plates scattered across, and the spacing between each copper trail is very wide, like 1.5 times the width of the copper trail. So it will protect good separation and reduce the neighboring effect, and hence increasing the Q factor. So to turn this into a loop, a coil with many turns, what we need to do is connect the alternate copper trail together. For example, the first copper trail, we connect it to this black wire. This will be our hot end of the coil. And then the second copper trail we solder with the first one here. And the third one here solder with the second one, and so on. So by doing that, it will create a coil of around 20 turns here. Then in the same way, we make the last two turns, that is the 21st and 22nd turn, for the S pole of the 3D cube. And this point here is the ground. So from ground to the hot end of the coil, we have 20 turns. From the ground to the S pole, we have 2 turns. Because this connection point is very fragile, so we have to solder it on top of a perf board like this. So this is part of the perf board. We'll solder onto it to get some support. Otherwise, if you leave it like that, this is very fragile and will break after a few moves. Okay. Next, we need to put in the jacket. So this is the jacket. Those you will see used by the people who need to work on the road. So it's reflective, like this one. So our coil will be like this, like this. Okay. Let's stick it onto the jacket, and this cable will be tapping on the shoulder, going back here. Then we'll attach our tuner, the crystal radio tuner, variable capacitor, the detector, and the headphone jack will be connected here. You want this to be closer to the top, otherwise it will be very hard to wear. Okay. Now how do we stick it together? You can use this type of silicone tape because it will stick quite hard. First. Okay, so I got one here, and then I'll stick it to here. This circuit works for both MOSFET, diode, or crystal. Let's walk through the MOSFET circuit diagram. You'll notice on the left that this is a loop coil. That means you don't need a separate antenna or earth connection. The loop itself will complete the circuit. As a big loop, you can just carry it out on the street. If you've got enough strong signals, it will receive those without an antenna and earth. So you just basically create a loop big enough with enough number of turns to create that inductance that can pair up with a 270 pF variable capacitor. If you've got other values of variable capacitor, you can just adjust the number of turns and the size of the coil to fit. Usually the bigger the size of the coil and the more the number of turns can be paired up with a smaller variable capacitor. We are using the MOSFET called 3DQ, which is a low voltage switching detector. It detects by switching. It is a modern way of creating radios that can run without battery. So this is a big loop crystal radio that can work without antenna or earth connections. That means you can move it around, nothing is fixed. You can carry the big loop on your body. In this case, we have a jacket to carry it on our bodies. This is very amazing. The first time I saw this type of big loop is on an umbrella radio that I created. I will carry the umbrella on the street and I can walk or run, and I keep receiving the crystal radios. This is really amazing. But for the circuit, the variable capacitor and the big loop coil together create a resonance circuit. Only the tuned station can resonance, and the combined signal after the resonance effect kicks in will be kind of enlarged due to the resonance effect. And this enlarged signal passes through gate number 2 to influence the current flowing from the source to the drain, S and D. Gate number 1 is a kind of a reference point, is connected to the neutral point of the circuit ground. The 20-second turn, which adds 2 extra turns from the ground, provide the source of voltage or current that flows through source, then to the drain, the D, and then to our earbuds, which drive the earbuds to produce the right signal or speeches according to the signal being amplitude modulated on the radio wave. Bottom line, this whole circuit, you don't see a battery or any source of power except the radio signals. You can receive any radio station without a battery. The audio jack is for you to connect your earbud or a headphone. It needs to be high impedance, so you can't use our conventional hi-fi headphone. It needs to be at least 500 ohm or above. If you don't have one, you can follow my other videos to convert a pixel electric buzzer into a very comfortable earbud that can work for this type of crystal radio. Now let's look at the circuit for a diode. The coil resonance circuit is the same. The only difference is the detector. There's only 2 terminals for the diode as a detector. The input to the diode is the 14th turn instead of the 22nd turn, because the diode has a different input impedance. For the output, it goes through the same low-pass filter, so only the audible signal will send to the earbud. Depending on your diode of choice, your earbud matching impedance will be different, usually from 5K all the way to 20K ohm. To allow us to match the output impedance of different crystal or diodes or MOSFET to the impedance of our chosen headphone or earbud, we can use a step-down transformer. There are many step-down transformers for crystal radios that you can get. One of the ones manufactured in China is called a KPB02. You can follow the instruction on my video to create a step-down transformer where you can switch the value for input impedance and the value for output impedance to match both ends, matching your crystal, diode, or MOSFET to your headphone or earbud. You need to connect a 100K to 1 meg ohm resistor across your earbud if you are using a piezoelectric earbud or any capacitance type earbud. The additional resistor allows a DC path for the diaphragm to release the charges and reset its form to default, and gets ready to make the next sound. I created a 3D printed chassis for this, but you can always use your own small boxes that can be put into the jacket. If you want to use this 3D printed chassis, you can follow the link in the YouTube video to download the print files. So once you got your chassis ready, drill the number of holes you need and mount the equipment, the component onto your chassis. But if you got the 3D printer one, you can design your own logo to make it more meaningful for yourself. There's also a slot that you can put in a cover. The front opening is for us to insert the terminal from the big loop. The first component we need to install is the plastic variable capacitor. Let's measure it with our LC meter. So we'll connect the terminal and we find the maximum capacitance is around 330 PF. There are 4 screw holes on my chassis. You just need to orient your VC in a position you can reach to the wires and the terminals easily. I designed this dial with numbers for the crystal radio. You can mount it onto the variable capacitor. To allow us to easily switch the type of detector from crystal, diode, and MOSFET easily, I usually use a 5-pin socket. Up to you, you can solder your detector of choice directly for better connectivity, less resistance, or you can do it like what I do here, using a socket, so you can experiment with different type of detectors to see which one works better under different situations. So if you use the 5-pin socket, you need to drill a hole, square hole to put in this socket. Next, we need to put a hole to mount the audio jack. This is a 3.5mm stereo audio jack. So you can mount it using this ring screw. Next, we need to mount this 4-pin terminal block for our loop antenna. So once you put it in place, you can use the screws there to secure the connection to your external loop coil. You can use the super glue or the hot glue gun to secure the detector socket and the terminal block for the coil. Since your variable capacitor comes with two gains, that means two different variable capacitor, all driven using the same diode, you can optionally put in a band switch, whether to shorten the two variable capacitor in parallel to provide a higher capacitance, or don't do that to keep the lower capacitance. This will allow you to work better with a big loop antenna. For the big loop, it is very hard to tune to the high end of the band of the medium wave frequency because of a high stray capacitance in between the turns of the big loop. You can fix this by having less turns in your big loop and adding a band switch, so you can increase the capacitance at the lower end of the band and reduce it at the higher end of the band. Look at the LH switch you see there. I'll do a fast forward on the soldering part. Next, let me insert my detector, MOSFET 3DQ. I usually solder it into a 4-pin header because the original component comes in a service-mounted device SMD format, which is very hard to use for a regular crystal radio. So it's better you solder it into something stronger, like a 4-pin header. This is how the 3D printer chassis looks after we insert the detector, and we now can cover it. So the detector, first 4-pin is for the MOSFETs, the 5th pin and the 3rd pin will be for the diode. So you can always change from a diode to a crystal to a MOSFET to see which one works better in your situation. Now let's mount the tuner onto our jacket. We can use the sticky silicone tape to stick our chassis onto the solder part of the jacket. Now we can insert the cables from the big loop coil. So if you use my 3D printer chassis, I have labeled it C for the cold end, S for the connection that goes to the S port, T for the tapping point for the diode, and then H for the hot end of the coil. So you just insert the cable in the right pin, then fasten the screws. Then you can insert your earbud with an impedance of 500 ohms or above. So this impedance I'm talking about AC impedance. That varies according to the frequency. It is not the DC resistance, which is fixed and measurable by a multimeter. So even if you have a 500 ohm impedance earbud or headphone, you can measure only around 100 ohm or below if you use a DC multimeter to measure it. So this impedance is different. You can usually see it from your specification. It's not easy to measure it. You need special equipment. If you can't get hold of a usable earbud for the crystal radio, try to make one following my instructions to turn a piezoelectric buzzer into a 2K ohm earbud. This will work with most of the crystal diodes as well as the MOSFETs. I'll put a link to that video into the YouTube description of this video. Let's check it out. Next, let's start the testing. So this is where I live. I'm just walking down this special road, which is very strong in terms of medium wave broadcast signals. Recording of this type of testing video is done through a special step-down transformer to be able to match the input impedance of the iPhone microphone jack. There are no other amplification involved, so it's a direct feed from my Crystal Radio to the iPhone's microphone input. I'll put a link to my YouTube description to show you how to make a step-down transformer for your smartphone recording of your own testing. What you're seeing at the background is the long bridge that connects the airport to the rest of the city in Hong Kong. It's called the Tsing Ma Bridge. My apartment is just across that bridge. After testing it, I find that a lot of people is looking at me with a strange pair of eyes. So it triggered me to think about how to improve this jacket to make it less outstanding and more stiff. Then I find this other jacket that I can make it stiff. Hide my coil inside the jacket and the tuner inside the pocket so I can tune it without being noticed. For the sake of making this testing video, I still stick the tuner onto the top of the jacket. But otherwise, you can hide it inside your pocket. And you can walk around testing the Crystal Radio reception conditions without being noticed. However, I still give this warning: don't wear this jacket into any sensitive area or in areas where you will be interrogated or even shot at, because people may worry that you may be carrying a bomb inside the jacket.
哦，原來二姑娘放假返嚟啊，真係好咯！呢次我有辦法咯。少奶，乜你話有辦法啦？冇事，我話接船有辦法啫，你快啲入去瞓先啦。哦。
This is the end of the video. Thanks for watching. If you like my projects, please click like, subscribe, share with your friends, and click the bell. Please also leave me some comments and feedback. Thank you.